the colleagues, I'm very happy to introduce our today guest. It's Professor Badreddine Assouar. Professor Badreddine Assouar received his PhD degree in materials physics from Nancy University in 2001. And in 2002, he became a research scientist at the CNRS. Yeah, it was in France. And he obtained the accreditation to supervise in 2007 and became the research professor. In 2010, he joined the St. George Institute of Technology in USA as a visiting professor, where he spent 2 years. And since 2020, he leads an acoustic metamaterials and photonics group at University of Lorraine. Yes, so he's developing the research on acoustic elastic metamaterials, metasurfaces, and even photonics. Yeah. So, and Professor Badreddine Assouar is editor in JASA, in Journal of Applied Physics, and in Scientific Reports. He's also an expert scientist in NSF, yes, in the National Science Foundation of USA. He's author of more than 100 papers. He's a real expert in acoustics. And moreover, I would like to add that Professor Badreddine actually already visited our university, our department. I think it was around maybe 5 years ago, around
2018.
Maybe even
2018.
2018. Yeah.
18, so, yeah, July 2018.
I joined his seminar. It was about acoustic absorbers. Yeah, it was absolutely great.
Yeah, so, we can contextualize this work to see the other advances.
Yes. So Professor Badreddine, so the stage is yours. Please, welcome.
Thanks for this nice introduction. I'm really thrilled to give this seminar, to be online for this seminar. So first of all, I would like to thank the organizers for giving me this opportunity, especially Andre, Misha, and Maria. So today I'm gonna talk about the acoustic. I just have one small request. I think the microphone should be muted somewhere because I have some feedback on my ears. Maybe it's the main. So anyway.
Yes, Andre.
So, yeah.
Yes, Andre, please. Okay, thanks.
Okay. So yeah, I'm gonna talk about metasurfaces and metamaterials, and especially from the acoustic side. Maybe elastic. So I did remove some elastic works because it will take a lot of time. But mainly, I'm gonna talk about acoustic metasurfaces and metamaterials for controllable wave manipulations, and especially to describe some recent works we have developed in the group and some main applications we can develop in terms of the acoustic metastructures in general. There are a lot of applications, so I will just delineate a few of them, but we can talk about the other ones. So the menu of my talk is pretty simple. I'm gonna introduce extremely briefly the concept of metasurfaces, which are very known, and you are extremely familiar with this concept since you are working on this. And I will develop three parts in this talk concerning the acoustic absorption. And I'm gonna start with the very similar work we did like 8 years ago and what we have done later. I'm gonna talk about acoustic holography and how we can construct acoustic hologram and multi-hologram, which we call multiplexed meta-holograms. And we'll conclude by talking about multifunctional metastructures. And I will give the example of the ingenious acoustic metascreen, which means how we can generate two different functionalities on the same metastructures, depending from which side of the structure we are irradiating acoustically the metastructure. So let me first just briefly, because I like introducing the acoustic metasurfaces, but the physical principle that they are based on, which are the generalized Snell law that actually add that term compared to the classical Snell law that attests that if we have two media and we can introduce an extreme thin or subwavelength thin layer between two media, we can then, by which we can introduce that abrupt phase shift on two phase range, we can actually manipulate the pad of the acoustic or elastic or optical propagation in very precise manner. So if I would like to, because that concept now of metasurfaces is really extremely used, sometimes properly, sometimes a little bit less. So if I would like just to give, it's not the exact definition of acoustic metasurfaces or metasurfaces in general, but if I would like to give just a very brief definition, it's a kind of 2D material. It's not really 2D materials, but in the sense that it's a subwavelength thickness and can provide or able to provide a not trivial phase shift over a 2 pi window or acoustic or extraordinary sound absorption. So that's being said, so for acoustic, for example, or acoustic metasurfaces, we can generate different functionalities and different properties, and it depends on what kind of wave physics and wave physics applications you would like to tackle on. So of course, in wave physics, you have three main functionalities. You have the reflection. So you can have different kind of applications. For example, here, some colleagues from Nanjing University developed this work about Schroeder diffuser. That's the classical Schroeder diffuser that you can find in theaters and things like that in order to manage the reverberation and the reflection of sounds. They developed the same system, but not based on classical Helmholtz resonators, but they use kind of Helmholtz resonators to develop a very thin acoustic diffuser or Schroeder diffuser based on like metasurface concept. You can develop also what we call a retroreflection. You send a wave from one side and you get the reflection exactly on the same directions. Of course, focusing by reflection. The second functionalities is about all the application concerning transmission. For example, acoustic lensing or super lensing. For example, here the acoustic holography. I will talk about this work a little bit. We can also manage to shape the path of the acoustic wave or the acoustic propagation in a very specific way. For example, here we demonstrated a few years ago that we can circumvent an obstacle, for example, for biomedicine application, if you would like to probe or to treat some specific organ and you would like to avoid, like, for example, some bones or something like that, you can design the path propagation of your acoustic beam in order to avoid any obstacles you want. So that's kind of things we can think about. And of course, there are absorption. This is the third functionality we can target. And this is, I would say, the most popular topic and application in acoustics, because acoustic absorption, and especially in the low frequency regime, is extremely appealing and extremely useful, because you can apply that in transportation, you can apply that in aeronautics, in aerospatial applications, in building engineering. So there are a lot of applications that acoustic absorbing metasurfaces can be useful for. So there are the three main applications or functionalities acoustic or elastic metasurfaces also can deal with. So first, I'm gonna talk about the acoustic absorption, because we've been working on this topic since a while. I have presented, I guess, in 2018 when we visited ITMO University, some very first work. I think the general idea of acoustic absorption is that, which is very different than electromagnetic metamaterials and optical, because usually in photonics and optics, we are dealing with much higher frequencies. In acoustics, we are dealing with very low frequencies. And the fact that when you deal with low frequencies, you are dealing with very large wavelengths, especially meter or few meters. The idea is how we can deal with this kind of propagation, which means meters, wavelengths with very small structures. So that's the challenge. And so the question is, how to tackle the challenge of low frequency absorption using very thin or ultra thin structure. So this is a very famous absorbing properties of the very known melamine foam, which is actually used in the Dreamliner. So here you have the acoustic absorption versus the frequency for different thicknesses of this foam. And as you can see, if we deal with a little bit higher frequency, which is above, let's say, 1 kilo or even above 500 hertz, it's fine. If you have like a 10 centimeter thick foam, it's fine. You can get like 80%, 90% absorption. However, when it comes to this very extremely challenging frequency range, which is basically below 300 hertz, even if you take 100 millimeter, 10 centimeter thick, you cannot get more than 10% or 20% of absorption. So this is a real problem. And the idea is how we can use artificial materials, which are metamaterials or metasurfaces, to deal with that. So this is a very old work. This is our first work. We published it in 2016. So we basically did that in 2015. We came out with this kind of acoustic sink. It's not really an acoustic sink, but it works like an acoustic sink, which is actually a perforated plate with a spiral, with a coiling channel. And then we have came with this. It was just theoretical, actually, but it was an impactful work to show that we can, with like 1 centimeter thick, it was exactly 12 millimeter, to enhance full absorption, perfect absorption in 125 hertz, which means that the thickness of our metasurface is 1 wavelength over 223. So based on this work, we have developed a lot of other works in order, experimentally and theoretically, in order to see how we can deal with this concept of absorbing metasurfaces in the real applications. But let me just make like a comparison between what we can call traditional acoustics, which is the most classical acoustic absorber development since a while, since maybe 100 years, about the micro-perforated plate. This is a classical acoustic absorber. It's usually based on perforated plate. You have an airbag chamber and you have a hard boundary. It's a resonator, because if you would like to enhance absorption, you need a resonance. And typically, the resonance is related to the thickness of this air cavity, which means that if you would like to use this concept to absorb a frequency about 100 or 200 hertz, so it means that you need a thickness about like 2 or 3 meters, which is not practical. So that's why this kind of solid ultra-thin metasurface, this is another work we have developed based on the very first one with a labyrinthine channel in order to go toward low frequencies. So this kind of system is interesting because in general, if you would like to enhance an absorption, or if you would like to get a perfect absorption, you must simultaneously realize 2 conditions. The first one is you need a resonance structure, you need a resonance. And the second one, you need a perfect impedance matching between your system, your metasurface, and the surrounding air, which is extremely difficult to realize based on the design and things like that. So that's the 2 conditions that must be realized simultaneously in order to get a perfect absorption. So that's what we did for different structures. So here, for example, we developed that in 2019, 2020 about these labyrinthine systems, theoretically, experimentally, and numerically. It's very low cost. That's one of the advantage of acoustic. I would say it's not a real advantage, but of the easiness, because if we are dealing with higher frequencies, like in photonics and plasmonics, we need usually to get this fabricated with micro-nano fabrication, which means clean rooms and all these very difficult processes, which I used to use a while ago. And here with the development of 3D printing and additive manufacturing, it's really very easy. If you get to realize the good structure, the good design, it's pretty easy to fabricate. It's another question to make measurement, because measurements is usually a little bit challenging too, but at least fabrication is extremely easy if you have very good printers. So that's what we did. So here you have an absorber of 13 millimeter working at an extremely low frequency at 50 hertz, which is actually the lowest frequency that exists right now. So we did lower than that, but it's one of the lowest acoustic absorber in terms of frequency we have realized. It. The problem of the absorption in low frequencies is that when you get to low frequencies, the resonance is extremely sharp, which means you have usually a very narrow band. That's a problematic because usually you need to realize that broadband feature, which is extremely difficult. The balance in general, there are three key problems in acoustic absorption and three features that we need to realize simultaneously. We would like low frequency, we would like very low thickness, and we would like broadband aspect at the same time. This is extremely difficult, but we are working on that because here we have a very thin metastructure or metasurface, and we have a low frequency, but we don't have the broadband aspect. So of course, we realize this, we put that in a waveguide, and we make measurement based on dual impedance tube or BNK structures and so on. So here, this is one of the very easy approach to enlarge the band gap or to enlarge the bandwidth, which means just by overlapping effects. Since we are in extreme subwavelength range, we can make like a supercell, which is a multiple unit cell, multiple absorbers operating at close frequencies, which means one operating at 50, the other at 52, 54, and so on. And by overlapping effect, we can do that. This is one of the simple strategies we can have, and we still will be in subwavelength regime. We still can make like a panel, a huge panel to put that in a wall, and it can work in a decent way. But still, it's a kind of local coupling between neighbor unit cells, and by overlapping effect, we can do that, and everyone can do that. But I will come back to this problem about the bandwidth and how we can enlarge the bandwidth, at least in terms of principle. We have also developed, because as you can see, as you can understand, and it's the same thing in optical metasurfaces, the metasurface is a structure, a rationally designed structure, which means that the properties are in general, not exclusively, but mostly defined by the design. It's a material by design approach. It means, especially in acoustics, it's the design which actually control the properties, because as far as we design based on hard material or solid materials, which means acoustically stiff material. It means any solid materials has a huge acoustic impedance compared to air. So actually we can guide the waves. So the design is extremely important when we work on acoustic metasurfaces. So that's why we have developed some deep learning approach based on CNN, for example, convolutional neural networks. So that was the work of my former PhD students. So we thought how we can optimize, how we can get with a new structures based on coiling up space geometry, and with the conditions that we need a perforated plate and a kind of coiled channel. So we set what kind of properties we would like to have. For example, low frequency. We set the condition that we don't want like a thickness higher than like 15 millimeter, 1.5 centimeters. And we developed that CNN model. It takes time, a long time, because it needs a lot of training, but it needs also to have a very solid and stable other numerical approach like finite element or other approach in order to train your model. And once it's trained, well trained, it's extremely fast. It's even faster than by far than finite element method. So I will not go to detail. I will provide the paper on that. So basically, we use 10,000 finite element simulation, 8,000 for training, 2,000 for validation, and we developed this kind of architectural network in order to come out with some very complex design that we cannot just think by ourselves to this kind of design. For example, we cannot just, okay, I will make a labyrinthine structure like this based on our knowledge. This is impossible. So this is generated by, for example, and the perforated hole on the corner. So this is something we cannot really imagine just by thinking on things like that. But anyway, we have developed those kind of approach to come out with some optimized structures. So here you can see the results where we can get even lower frequencies, about 40 hertz. The problem we have, it's still the same. We still have a narrow band for the absorption, but we expected that because we are in the extreme low frequency range. We have a very thin metasurface. It's wavelength over 684. At those kind of frequency, the wavelength in the air is about 6 meters. So being able to absorb 6 meter wavelength with like 1 centimeter acoustic metasurface is really very interesting. So that's some things we have developed too. We did the experimental verifications. So here I'm just showing another structure to show how the structure is designed inside, but the absorber should be, of course, closed. And here we have, for example, the absorption of these metastructures so the comparison between CNN and experiment. So this is a different than the first one, which was operating at 40 hertz. Why? Because actually the impedance tube we have in the lab, the limit of the operating frequency is 50 hertz. We cannot measure anything below 50 hertz. Otherwise, you have a lot of noise and things like that. We need to purchase like very specific tube and equipment for that. So we used CNN to demonstrate that, okay, we can go for very low frequency regime, but we changed a little bit the design. As you can see here, the hole is not in the corner, is in the center, just to show that CNN is able to generate some complex structure that could be very interesting. So that's the thing. So one thing I would like to mention here, I talked about before, it's the no locality. So this is a concept you guys know very well, because it's a concept coming from...
I'm sorry.
Yeah.
But before we go further, can I have a question on the last couple of slides?
Yeah.
Right. So am I right that you have? So first question is technical. Is there a hole? So is it a closed?
Yeah.
And there is only one hole, right?
Yeah.
Or
yeah.
how does it? So sound penetrates through that hole, and that's it.
Yeah. Yeah. So yeah, I didn't explain this. I can explain it if you want, but go ahead for the second question if you want.
Yeah, the second is so what exactly gave you the numerical simulation? I mean the like this optimization.
Okay, so
like if you still have the narrow bandness, and so the lambda over the thickness, what was the
I'm not sure I get the question, because sometimes I lose your voice, but can you repeat the second question, please?
So what is the profit of doing this numerical optimization? What did you earn from that? Because again, you have narrow band.
Yeah. So for the first question, so I said that it's a kind of acoustic sink. Actually, if you have your metasurface, this is it actually, one of this. Okay, can you see me? Yeah, with the hole in the center. So if you have this absorber and it's impedance matched with the air around, so when the wave is coming like this, actually, the wave will try to find the easiest way to propagate. It will not be scattered, it will not be reflected, because it's impedance matched. So they will just be, it's like water with a sink, it will just try to reach the easiest or the lowest impedance, which is the hole. So the idea is to trap this acoustic wave. So the wave will be guided to go inside the hole. And if they are trapped by the hole, they are forced to go inside this labyrinthine channel, and then by thermoviscoelastic effect, you can enhance absorption, and all the acoustic energy actually is dissipated in thermal energy. This is the first question. The second question about the CNN, actually what we earned is that the idea was how we can go toward lower frequency than what we get, about like 60 or 100 or something like that. And we were hoping that maybe the structure that CNN can propose us can simultaneously give us some lower frequency, which actually it did give the 38 hertz. But we were hoping that maybe we can get broadband, and we didn't get it. But still, it's a very important approach, because if you have a stable CNN, it's by far much faster than finite element method. It's a fraction of a second, so it goes very. So that's the idea. If you have a stabilized one, even if you don't want to have like optimized structure, you have a very fast approach to calculate the absorption coefficient of your structure or other design. Okay.
Okay. Thank you. And the very last from this part. So you already thought about that you could do a multi-layered structure. Yeah, but that's again will provide you additional thickness, of course.
Yes. So one of the main requirements for us is that the thickness is something we don't want to change. So that's the thing. Okay, 1 centimeter, 1.5 centimeters, 2 centimeters maybe, but not thick. Otherwise, it's okay. We will go to, but I will explain a little bit this on this. If I can move on the non-local things very briefly. So non-locality, this is a concept you know very well, that's come from optics, and the idea is very simple. It's how we have local effects. That's what I talked about before. So you have like supercell, and you have different unit cell, and you have the coupling with the neighbor. But here, non-local effect, of course, it's beyond the nearest neighbor. And what we did with a different structure, it's not conic structure, is just to see what non-locality can bring for absorption. And what we developed in very simple acoustic system. So we have just a straight channels. Okay, it's like helmet resonator with different length. You can see here unit cell. This is a tree of this unit cell, and these channels have different length, which means different resonances, and by coupling we can enlarge. And if you see this is a black, you see the subscription is black, this is orange. The black is the absorption coefficient here. So it's just simulation for now. So we can see that, of course, we have a large band gap, but of course we are not in the extreme challenging low frequency. We are like above 500 hertz, which is still challenging, but not as challenging as the other ones. So we can get broadband, no problem, that works fine. But the problem is that the thickness is a little bit higher. Why? Because actually, if you see the conventional theory, the quality of absorption is related to what we call surface filling ratio. Here you have surface filling ratio is quite high, it's 0.7. If we would like to reduce the thickness, what we did, we took those channels and we bend them in order to reduce the thickness, okay? But if you reduce the thickness and you take the same tree unit cell as a supercell here, you have low filling fraction, but of course you have smaller thickness, but the quality of absorption is the orange curve. You can see that we lose a lot of absorption. So the balance or the question is how we can simultaneously get that higher absorption, but with small thickness, which means with low filling fraction. So we just developed a very simple structure based on those channels. So here you have 3 different structures. So here you have folded bridge, okay? Here we have the folded bridge with some cavities. You will see why we put individual cavities. And here we have the same folded bridges or channel, not bridges, sorry, channels. But we put a bridge to connect all the channels, which means that we would like couple channel 1 with 3 and with 4 and so on. You understand that non-local coupling actually. So this is the lamped model. And here, if you see O, C, and B, you have classical coupling in these 2, which are non-local effect. And here we have beside the classical local coupling, we have non-local coupling introduced by this bridge. Actually, we added that example in order to simulate a little bit some kind of, adding cavities. It's a kind of bridge not connected. So it's just to have a better comparison. And we simulate this and we fabricate also the structures. And here you have the three structures. The first two, O and C, are non-local, and B and local. Okay, we fabricate this. It's the thickness. It's about 6.8 centimeter. Again, here the idea was just to see the effect of non-locality on the absorption. And you can see here different curve, simulation, and experiment. But just focus on the blue one. The blue one is about the non-local effect. The continuous line is the simulation, and the dashed line are the experimental. So we can see that we have pretty large band of absorption from 550 to like 2070 hertz, and the quality of absorption is about 94%. And of course, all the result we get from this non-local effect are much better than what the considering just locality actually introduced, which means that we have a real added value that no locality can introduce on that. So we can get really very good quality absorption on a large band. And if we compare this, that was published in 2021, and we compare this to one of very famous work from Ping Sheng groups. Ping Sheng, for those who knows, he's in Hong Kong University of Science and Technology. He's retired, by the way, now. He's in England, so but he's still active. So if this is a paper appeared like in 2017 in Materials Horizon, and what he did in that paper, he just make fabric pure channels, and he folded some channels and this kind of things, and by overlapping effect, he got a very good broadband or broad absorption. But this system, it's about 14 centimeter. And if you compare, this is not optimized. If you compare with this one, we have almost the same bandwidth, but we have less than the half of the thickness. The idea here is just to see how non-locality can be very interesting for a kind of absorbing metasurface. So now we are working, which is we didn't publish that yet, how we can combine actually the non-locality effect with the former structures I showed before, with the former structure based on those labyrinthine channel and things like that, to see what we can. And we get some very good results, but we are still working on that and didn't publish that yet. So of course, this is some oblique incidences we have done. I will go a little bit faster now. So this is just to show how non-locality can improve the oblique incidences for absorption, because all the results usually we make, the measurement we make is for normal incidence, because we are in like a waveguide in a tube, so we have just like normal incidence. So if we introduce non-locality, we can also improve the oblique incidence absorption too. So that's for the first part. I don't know how much time left for me to see how I can go a little bit faster or not.
So at least 25 minutes.
Okay, good. Okay. So let me now introduce some works we have developed also on holography, or how we can generate acoustic holograms using.
Professor Badreddine, may I ask a question for the first part?
Yeah, sure. So we can actually discuss on this part first. Okay.
Have you checked how your structure works for different angles of incidence?
Experimentally?
Yeah, experimentally.
No, we didn't, because the experimental setup to do that, it's quite heavy, and we didn't do that. But we did check for normal incidence, which actually agree with the numerical calculations. So we do think that because we validated for normal incident, it should be fine for experimentally for oblique incidences, but we didn't check for oblique incidences experimentally.
Okay, thank you.
Any other?
Yeah,
Go ahead.
maybe I can ask a question about this labyrinth type structures. So, I mean, yes, this one. So you told that the dissipation is in thermal energy. Yes, am I right?
Yeah.
Mostly. So, and I mean, as far as I understand, it is mostly related with thermoviscous losses in these channels. Yes, and
not only, but yes.
I mean, partly. So, in this sense, I mean, as far as I understand, so the smaller the width of the channel, so the larger will be the thermoviscous losses in this channel. So, is this?
It depends on the frequency too. So.
Yeah, so I mean, is this is there any balance between the widths of the channel? So
yes, yes.
If it's too small, so you will not reach the effect, and if it's too large, you also will not reach the effect. Yes.
Yes, because with the frequency, you define the thickness of your thermal layer and viscous layer.
Yeah.
You have to consider that. So you see the continuous temperature, let's say, between your fluid, the air, and the hard boundary. So the thickness of the viscous layer and the thermal layer depends directly to the frequency, which means to the wavelength. So you have to consider that in your design, in your program, in order to see. So for example, if I consider smaller channel in terms of width, I will not get the same frequency of resonance and the same frequency of absorption. And I will not get the same quality of absorption too. So there are a lot of balances between that. There is also a balance about the diameter of the hole, which is extremely important also for those friction in the end. So we did also some other works with the hole, but it's not the perforated hole. We added like an aperture. It's like a small tube to play with the acoustic impedance. So there are a lot of different geometrical parameters to deal with. The other things I would like to mention, the absorption is not only depending on the thermoviscous effect, but is also depending on the fact that when you create this kind of labyrinthine structure, you create you mimic a kind of high refractive index material, because that's what you create an effective media actually. And the fact that, for example, if you have 2 points, you have here a source and you have here a microphone, and you don't have anything in between, okay? And you send your wave from the loudspeaker to the microphone. Okay, the wave will come after 1 second, let's say. And then I hide this part, you cannot see it, and I put like a labyrinthine channel, hard labyrinthine channel, and they send the same wave. So this wave actually, that's the principle of coning of space geometry. This wave will take more time to travel in that pad to arrive to the microphone, which means it will arrive, let's say, about 5 seconds. Okay, it means that you created a kind of media that slow down effectively the phase velocity, the effective phase velocity. And then you mimic a kind of high refractive index, which means that you introduce first a very an extreme dispersion in your media. Okay, you have some extreme properties. And second, because you slow down this wave and because you have thermoviscous effect, you dissipate all your acoustic energy to thermal energy to heat. And the heat, it's not that much because the heat, so you cannot feel it actually. So that's the basic principle. So to design this, it's not that simple, because other than the physical parameter about thermoviscous effect and all the things, you have a lot of balances to find in geometrical ones concerning the perforated plate and the labyrinthine channel, the thickness of the wall, the larger of the channel, how the labyrinthine is structured, and all this, how this cavity, for example, is larger or not. So there are some balances to find.
Thank you.
So I also have a short question. So at the previous slides, you showed that the absorption spectrum, but measured for metasurface. So and we see some perfect absorption, yeah, coefficient 1. But if you consider just single meta plate, what would be the absorption cross-section in terms of geometrical cross-section of this meta plate?
What do you mark a meta plate? Just like a bare plate?
Well,
What do you call
this meta atom? This meta atom. So if you consider this meta atom in vacuum or in air, and measure the absorption cross section, so and normalize it to the surface area, what would be just absorption cross section in terms of geometrical cross section of this plate, of this meta atom?
Difficult to say, because it depends on the frequency, which means the wavelength, and you cannot consider just the unit cell.
In resonance, I mean, it's so if just single.
Yes,
single,
if it's a resonance,
yeah,
it would be, yeah, the exact absorption of one unit cell of the single I am showing here. That's what you will get if you have, or in terms of cross section, you will have 100% absorption.
No, I mean, it's just
is it this your question?
No, just one meta atom.
What do you call meta atom? This is meta atom for you?
This one plate, I would say, this one plate. So this is our A to A size. The size is A square A to A.
Yes, yeah.
Just one
yes.
in air, and you have some just plain incident wave. So of course you will absorb a finite amount of energy.
Yeah.
So,
but you have you have boundary effects, you have edge effects. So it's difficult to say what would be in like a piece, like a room like this. You put just 10 centimeter by 10 centimeter, you send wave. Yeah, you have some cross section, but you have some problem of boundaries too. So you cannot really consider it just alone. For example, if you would like to isolate a room, you have to put the absorber on all the wall. Other than that, so yes, it's like exactly like foam. So if you have in every building, you put like a layer of foam, or I don't know, something like that. You don't put it just in one location. You put it on the wall. For example, in airplane too, airplanes, they have this kind of foam on all the fuselage. So they don't have it on specific locations.
Okay, I see. Okay, thank you.
Other questions maybe on this absorbing part? Okay. So yeah, I'm gonna talk a little bit about the acoustic holography, and in two ways, in how we can generate and form acoustic holograms by transmission and also by reflection, using the reflective metasurfaces and transmitted or transmissive metasurfaces. So let me first introduce one of the first work that has been done on meta hologram by using what we call the simultaneous amplitude and phase modulation, because the classical work in general, if you know all the acoustic holograms based on traditional acoustic, usually they use just sometimes the phase modulation. So one of the very first work that used the amplitude and phase modulation has been done by some colleague from Nanjing University, the same who developed that Schroeder diffuser I talked about in the very beginning. And they developed what they call a lossy acoustic metasurface. So they introduced some loss in order to modulate the amplitude. And it's a reflective metasurface. And here you see APM simulation, which means amplitude phase modulation, APM experimental. And if they compare that only with phase modulation, they got pretty much better hologram, acoustic hologram. And the idea is simple. With the reflective metasurface, you have your metasurface here, and you send a wave from a specific angle, and by reflection, you project your image, your holograms, which is pretty complicated, but still, it's very interesting. So what we've been inspired from this work, and we decided to develop what we call multi-holograms or multiplexed holograms. So it means that how we can, by the same metasurface, by the same meta-hologram, how we can project different holograms at different frequencies with the same metasurface, and using, of course, the amplitude and phase modulations. So here you have a specific acoustic metasurface. I will talk about the design of this metasurface. you have loudspeakers emitting different frequencies, and the principle is like this one. You send different frequencies, by reflection, you project 4 different holograms at the image plane. Of course, no. Of course, here we introduce leaky loss, okay, in order to modulate the amplitude. And of course, the design will actually modulate, as I will show, the phase. Okay, we have here an absorbing panel. So that's the idea, sending different frequencies and by reflection, getting the holograms. So how to construct these holograms? It means that holograms is acoustic pressure. It's defined by a specific phase and specific amplitude. So first, we have to define at what distance from the metasurface we would like to project our hologram, let's say 4 centimeters, and we will define our image we would like to project. So every image is composed of 4 different pixels, and every pixel is a specific pressure, acoustic pressure, with specific phase and amplitude. And by time reversal, we will calculate what kind of pressure we should generate at the surface of the metasurface. We pixelize the metasurface, and we will calculate what kind of specific phase and amplitude should emanate from this metasurface with a specific distance to get those images, those holograms. So that's what we did. Now I will describe the composition, the design of this metasurface. So what we did, because we are working on a reflective metasurface, the best reflector is Helmholtz resonators. So we developed this kind of unit cell. You can see here, it's like a channel with 4 different cavities, 4 different Helmholtz resonators. Of course, these 4 Helmholtz resonators have different resonances, which means different frequencies, which means different reflective frequencies. And we manipulate or modulate the amplitude and the phase based on 2 geometrical parameters. It's the position of the Helmholtz resonator, as we will see on the channel, and it's the height of the Helmholtz resonator, its dimension actually. And it's pretty easy. And of course, every unit cell here, you can see here, every unit cell here, it's actually what composed this. So the unit cell is like those channels, it's in the perpendicular. So every unit cell here is what you see here, okay? It means that you have the incidence coming from that side, and you have the reflection from the same side. And let me explain how it does work. So here you have, for example, the amplitude versus H1, and here you have the phase versus P1. H and P is the height of the resonator. I'm just talking for one frequency, and it's the same for the other one. I'm talking about the first frequency, 3,500. So if I take the C1, which is the Helmholtz resonator acting on frequency 1, I will just change its position on the channel in different location of the metasurface, or I will change its dimension, its height. So if I change the height of this resonator, you can see that I can modulate the amplitude, okay, with different parameters, with different values. However, of course, the other frequency doesn't change because I'm just acting on one resonator. Now, if I change the P, the position on this Helmholtz resonator on the channel, I change the phase shift from 2 pi to 0, okay? Which means that I have 2 parameters, 2 geometrical parameters that both act on the phase and on the amplitude. They are not completely decoupled. So what we did, we defined 3 different value of phase, 3 different value of amplitude, as you can see here, and we made like a matrix. So here you see how the amplitude behave as function of different H and different P, different height and different positions. If you can see here, if I change the position, okay, if I draw like a horizontal line here, if I change the position, actually the amplitude doesn't change. However, if I draw a vertical line, if I change the H, of course, the amplitude change. And it's the inverse here. If I draw a horizontal line here, it means that I change the position. I see that the phase change from blue to yellow to red and so on. It means that we will have different combination between phase and amplitude, okay, that will give us some very specific pressure. So what we did, we defined, as I said, 8 value of the amplitude, 8 value of phase, and we constructed 64 combinations, P1, 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 A1, P1, A2, and so on, that give us this the pressure we need on the hologram plane to project the hologram, and it works. Actually, it worked, because you can see here some of the example we have done. So this is what we wanted to plot, what we want like to project, and we got some very good definition of, for different frequencies, we will be able to project different images at different frequencies with this reflective metasurface, and we got some more complex images, and we were able at different frequencies with the same metasurface to project this hologram. Of course, that was just numerical and theoretical, but we wanted to show that experimentally, and we say, okay, let's see now, because in the reflective metasurface with hologram, it's not practical, because you have here your metasurface, you have to send your wave in the same part as the reflective wave, which means it's not practical. You can have some problem of interferences and so on. However, with the transmissive metasurface, it's more practical, because you send your wave here and you project the holograms in the other side, but it's by far more difficult. So that's what we try to do with the transmissive metasurfaces for acoustic holography, based on simultaneous modulation of phase and amplitude. So this is the general structures. It's more complicated. The idea is to send different frequencies on a metamaterial on metasurface, and to give a projection on different holograms. So of course, the unit cell is by far more complex. It's composed with 3 parts. From 3 parts, we have a coiled, a kind of labyrinthine, a kind of coiling up space things, which means actually it will modulate the phase, because we will just delay the wave or not. So it's obvious that the resonator that will modulate the phase should be like labyrinthine. It's the red part. We have the modulators. It's a cavity that will actually act on the amplitude, less or more amplitude. And we added a cavity that will act on the frequency we will select. So the unit cell actually is composed with 3 modulators. And it's a little bit complex, because it's very sensitive to the geometrical parameter. You can see here PM. We can modulate the phase with the labyrinthine structure with different parameters. AM, amplitude, we can use the H1, the height of the cavities, and of course the FM, which is the frequency modulation. Also, it depends on the geometrical parameter of this modulator. So I will not go into the details. Here you have the numerical and experimental result. Different amplitude, the transmissive amplitude, and the classical amplitude. Actually, it's the amplitude, the transmissive, it's what we get in hologram plane, and the classical amplitude, it's what emanates from the metamaterial plane. So we got some pretty good result, and we fabricated the structures, and that's the figures I showed in the very beginning of my talk. We have 2 different holograms. This is the simulation, this is the experimental. We made the simulation at different distance from the metamaterial plane to hologram plane or hologram projection, and we found that at 5 centimeters we can get very good results. So we reproduced that experimentally, and we can project by transmission 2 different holograms based on 1 metasurface. We can do that for more frequencies, but it's a little bit more complicated, because the unit cell should be a little bit more complex to do, but it's doable. And we did also other things with this kind of simultaneous modulation of amplitude and the phase, how we can generate, for example, annular panel pattern, how we can generate focusing, really high quality focusing on 2 different spot and 2 different frequencies, which is extremely interesting for all the biomedicine applications, for example. So that's the end of the part concerning the acoustic holography. So if you have any any question in this part, I would be happy to answer your question before going fastly to the last part of this talk. Okay, so I guess no question here.
Maybe a short question from me. So how do you think, is it possible to go to some modulated structures, so mechanically adjustable metasurface? Did you think about that?
Mechanically adjustable. You are talking about reconfigurable mechanical structure,
right. Right. Just if you could some kind of a control this control the metasurface to change the image, to change the phase mask, at least, like to modulate the phase somehow.
So the phase you can modulate it. Yes, maybe, because the phase is related to the delay. So if you can change kind of space, inside space or outside space, reconfigurable, normally it's doable. It's something that we can envision ingenious.
Okay, thanks.
Okay. So let me go to the ingenious metasurface. So that's something you know very well. Ingenious is coming from the yes, of course, for metallurgy, but it comes actually from the chemistry community who developed many years ago. I don't know how many years, the ingenious particle or microparticle with that B functionality, which means that you have one property from one side and the other property from one side. That's what we call everything now ingenious. And to develop ingenious acoustic metascreen or bifunctional acoustic metascreen, we've been inspired from this work from CQ from Singapore, from NUS, who published that paper in 2020 about EM metasurface, optical metasurface. And the idea was very simple. He developed a design, and if you irradiate from one side, you have one hologram, specific hologram, and from the other side, one other different holograms, and which is actually a ingenious metasurface. And we've been talking about how we can do that in acoustics. And the thing is that how we can not only produce the same functionality, which means holography with different hologram, but how we can produce different functionalities. For example, from one side absorption, from the other side, I don't know, negative refraction or focusing or something like that. It's just to change the functionality, not just to have the same functionalities plotted in different ways. So what we did is that, okay, how to implement different functionality in the same metasurface, how we to implement or to put forward a ingenious acoustic metascreen, because a ingenious metascreen can realize one way or two side wave manipulation. So it means that your structure, your metasurface, of course, should be non-reciprocal from both sides, from forward and backward. So the physical mechanism is pretty simple. To realize a ingenious metascreen, you need to simultaneously, again, realize two conditions. First, you need to break reciprocity. Okay, so you should have no reciprocity from both sides, but you have, or you must also have, a full transmission from both sides, which is not the case of the classical no-reciprocal system. For example, if we take that famous acoustic circulator that has been widely used, published notably in that science paper by Allou's group in 2014, biased structure. So you have three-port, and you have like a rotor, and you have a fluid, and you reduce the rotation in one side or two sides. If you have here an open cavity, of course, you can see here the simulation of the transmission. If you don't have any bias, so you have a small transmission here because you have some leakage. You have some leakage, and if you manipulate your rotation in one side or two sides, you can either get a very full transmission or nothing, actually, a kind of reflection. Okay, so this is no reciprocal, but you cannot have transmission from both sides. So what we did is that we coupled two acoustic circulators, okay, and we considered here that three-port like a phase modulators, closed phase modulators, hard boundary, there is no leakage. Actually, it's the third port is closed. And we calculate here the transmission from both sides. You have simulation and experimental result. And of course, the system is non-reciprocal, and the system can guarantee transmission from forward and backward direction. So, okay, so now we have the condition to realize this. And of course, we can manipulate the propagation as function of the rotation of our fluid, of our air, of our rotors, and the speed, of course, and things like that. And the second thing I would like to mention is that we need to have no reciprocal phase modulation. And this phase modulator is extremely important because here we will consider two different phase modulator, two different age, two different cavities. It means that we can have different phase from every side. So let me explain briefly that. So this is the full picture of the one unit cell, two acoustic circulators with the phase modulators. And the idea is very simple. It depends on how you put your fluid rotating in the system. And of course, you don't have the same phase modulators. So here, if you stand away from this side and considering the sense of the rotation, you will have the propagation toward that port 3, not here. And then because here we have a hard boundary, we will have a full reflection, and then the wave will propagate in that side. And of course, because here we have the direction of the rotation in the other sense, you will have the propagation towards here. So there is no role of this phase modulator number 2. Okay, so all the phase will be controlled only by this phase modulator. However, and you can see here this properly. So you can see the blue. So the blue is forward direction. So you have the phase modulation. And if you see the orange part, which means the backward direction, you don't have any change of the phase. Here it's the same thing. The phase modulation from the backward direction will be only modulated by this phase modulator. So depending on the rotation, and then you can guarantee transmission from both sides and no reciprocity. So we have built this kind of structures. The unit cell, as I see, can realize the no reciprocal phase modulation because we have opposite rotating direction of our rotor, and we can design forward and backward phase profile. Because in acoustics, I guess also in optics, in order to realize specific functionalities, let's say absorption, splitting, negative refraction, I don't know, focusing, you have a specific phase profile. So if you can design independently the phase profile from each direction, you can generate by fact directly two different functionalities. The idea is just to design the phase profile you want and then to realize it experimentally, to design it, to fabricate the system that guarantee the phase profile you would like to do. So what we did is we get a lot of structures. This is one of them. With 15 unit cell, you can see here the connected resonators. You can see here the different motors that act on the rotor inside to make the spinning of the rotor in one direction or in the two directions. You have here, of course, the phase modulator with different height. We put that in a waveguide and we made the measurement. And here I will show you just a few measurements we did. And numerical. So here you have simulation, experimental, simulation, and experimental. So here, how we can generate negative refraction or extraordinary refraction in different ways. So if you send here a plane wave, here you have, of course, the ingenious meta screen. You send here a plane wave. We designed the profile here in order to have negative refraction. Now, if you take the time reversed, it's not the propagation like that. We took exactly the time reversed of this one in this ingenious meta screen, and here we have a negative refraction or extraordinary refraction. We don't have anymore that perpendicular transmission. You can see here the experimental evidence of it. Now we design other profiles. So for example, here we designed how we can make absorption from one side and focusing from one side. So if you stand here again, a plane wave, you get a focusing. Okay, we designed the profile here to get focusing. However, if you take here the time reversed, we take focusing like a point source in order to simulate the focusing. We take a point source, we have absorption. Why? Because we designed the phase profile here in order to have absorption, especially we just introduced loss, leaky loss. We just open actually the phase modulator, and all the energy went on these modulators, and that's it. So we generate two different functionalities, and we can do at will what we want. Here we have focusing from one side. In the other side, we have extraordinary refraction, or for example, and we can generate even two antagonist effects, diffusion and splitting. Diffusion from one side and the splitting from other side. All that to say is that as far as you can guarantee a full transmission from both sides, a full non-reciprocity from both sides, which means you can have that non-reciprocal phase modulations, you can implement any functionality you want from every side as far, because, not as far, but because you can design your phase profile and you can fabricate the system, the cavities, the circulator that guarantee the realization of this phase profile. So I think I'm done. This is just some of my students who worked in this work. So Ingenious Metascreen, it was mainly Zhu Absorption, it was mainly Kropali and Yuzhang, and now Marnix is working on Absorption still, but I didn't present his result because it's under progress, but he's trying to combine non-local effect with labyrinthine structures and other cavities, and he's starting to get some nice results. So that's it for me. I was a bit long, but I'm done. Thank you.
Oh, dear colleagues, please, questions?
Can I ask, please? Thank you for your seminar. I want to ask one question. Maybe I don't hear, or it's stupid question, but in the last part of your lecture, you say you use some motors, some rotors, some mechanism. So how noisy is it? Is it have some influence for experiments or something like that?
No, it doesn't. Actually, it's a very small motor. It's not really noisy. So we put them here in a specific cavity. I don't know if you see this. So it's a really very small motor. We purchased that on Amazon because we didn't find this in like a classical things. And yeah, there is no noise. So we cannot really have noise that could be or affect the results.
Okay, thank you.
Yeah, maybe one more question regarding this part. So here you consider some mechanical changes. Yes. Have you tried or thought about some like piezoelectric tunability, or I mean to get rid of the mechanical part? So some other mechanisms for the changes.
Mechanical part. The only mechanical part here we did change, if I would say mechanical part, is the height of the height of the phase modulators. So I don't know. Maybe I didn't get your question. How to implement piezoelectricity here? To modulate the phase, you mean?
Yes.
So maybe we can, instead of having like rigid phase modulators, maybe we can have something based on membrane or something like that, actioned by some piezoelectric effect in order to change the phase, maybe. But it means that it will be active, which means that we have to also to control this by like circuit or something like that. But maybe it's possible. So the idea also for us is, I know that we can do a lot of things with those patches and piezoelectric effect, but the idea also for us for the term of application is that we try to find some ways to fabricate and to design, even when we think about applications, to design structures which are as much as passive as possible. So that if we can do that like mechanically, or we're just changing some, it's a heavy structure. I understand that. Probably we can do the phase modulation in other way based on piezoelectric effect and membranes, for example, probably. But yeah, why not? I see that there are some questions also on the discussions.
Seems that Andrei tries to ask something, but we cannot.
Yeah, Andrei has some problems with the sound.
We cannot hear him.
He can hear us, but we can't hear him.
If you can write just a few words about the question if you have already, but we cannot hear you.
May I ask a question from Andrei's side? How to apply fetch acoustic holograms? Are there any applications?
Yes, the holography it's more about the biomedical application. That's why I mixed that also. Let me see. I mixed that also with the focusing by the end. You know, even in the paper, we've been talking a little bit about this, how we can to mix focusing, not super focusing, and how we can project. The thing about acoustic holography or hologram is that basically you project a specific design of acoustic pressure, which means that for treatment, for example, not for imaging for now, but for treatment, you can, if you have like ultrasound in different regime, ultrasound source, you can project a specific design of ultrasound on specific region of the body, but not touching other region. It's actually linked to what I said in the very beginning. Sometimes in the ultrasound treatment, you need to be extremely careful because you would like just, for example, to treat a specific zone without making, for example, you would like just to treat like annular regions. So we have just to project a annular hologram. So basically, it's more about this, about the biomedicine applications. So the other application we've been considering is actually about the acoustic levitations, because as far as you can consider holography and acoustic pressure, it's a kind of the classical acoustic levitation, actually based on classical acoustics, is very complex. It's a kind of array of a lot of loudspeakers with different orientation, and basically you generate what they call a 3D acoustic trap, and you trap like a very small particle, which is extremely active. It's a lot of circuitry. It's very complicated because you have to generate that acoustic pressure by different loudspeakers. Here we can, by one loudspeaker, generate different hologram, because we can generate these different frequencies, and we can construct some 3D acoustic trap using holograms, for example.
Mm-hmm. Okay, it seems that you can hear me, yeah?
Yeah.
Okay, that's great. Thank you for the answer, yeah. More questions, please?
Yes, I have a question about the first part, about absorbing metamaterials. Did you try to combine the metamaterial with poroacoustic materials, or is not reasonable for?
So no, we didn't. Other groups did. There are some papers since 4 or 5 years. People are combining Metasurface with some foam, with some, because the problem of that. Why not? the problem of that you make the structure a little bit more complicated, a little bit more thicker, and you have a problem, for example, about the boundaries, how in terms of application, how you can stick the foam with the metasurface, and it's a little bit complicated. So I know that there are at least 2 groups, one from Korea, from the Seoul National University. I think the paper is in extreme mechanical letter, something like that. And there is another group in China. I saw that before, at least 2-3 papers combining metasurface with foam and porous materials. So why not? But I don't think that we can have an added value in doing that about what exists. To me, it's either making a full system based on porous materials or foam or all those advanced chemistry materials that have some specific properties, or either doing that in terms of cost too. If you would like to deal with an aeronautical company, for example, they have just, for example, we are doing that right now. They are using a kind of foam. They would like to use material or metasurface. They cannot use both because for the thickness, for the bulky aspect, for the cost, for a lot of things. So to me, that's my point of view. I think it's interesting, but it will not really bring a real added value to the topic.
Mm-hmm. Okay, thank you.
Thank you. More questions, please?
Okay, can you hear me?
Yes.
Okay, hi. So it's very my pleasure to meet Professor Assouar again online, because I'm not sure whether you remember or not. We met before in Lamour University in Lamour.
Oh, okay, yes. Okay, when there was like France, China
many years ago.
Workshop. Yes,
yeah, many years ago. So at that time, I talked with you because we are HEU, Harbin Engineer University, and then we say if we have chance, we want to invite you to our university. So I think because of the COVID-19, so it passed many years. So today it's my great pleasure that we meet again. So let me introduce our university. Currently, we have another campus in Qingdao city. I'm not sure whether you heard about Qingdao.
Yeah, I heard about this from Andre.
Yeah. So Qingdao campus is actually a place which is faced to the international a lot of scholars from international. So now it's my chance to invite you again to Qingdao, our campus. Maybe we plan a summer school. It's not it's a training school about acoustics. Maybe next year. It's March, right? March.
In next year. First week of April. Yeah. We already invited. Yes, Professor Badreddine. Yeah.
Okay. Yeah. So I finally feel I realized my dream that invite you to our university.
Thank you. Thank you very much. So definitely I will consider that. Of course. It will be my pleasure to visit the campus. So we talked about this with Andre too. Yes.
Yeah, it's great. So regarding the Metasurface, it's my one comments. Actually, I read your paper published in Nature Material, right? So it's a very good review. But currently, I think about how about the application of Metasurface for underwater acoustics. Actually, we realized that maybe there's a great potential that Metasurface concept and also some functional devices have a great potential which can be applied in underwater acoustic applications. For example, to improve the underwater acoustic communication capability, as well as the underwater imaging capability. So probably, I'm not sure, because I don't see much paper about the Metasurface work published about the underwater published in very high level. Yeah.
Yes, actually, it's very interesting topic. We are not working on that because for us underwater, it needs a lot of facilities. So, for example, to me, the idea is when we at this stage of metamaterial and metasurface, especially in acoustic and elastic, we need every time to make like some experimental proof. So if we just publish things about numerical, it's fine, but it's not good. So there are some papers. There is one colleague from South China University of Technology. You maybe know him, John May Jun.
May Jun,
He did some, May Jun. He did some paper or two about this, but there is a very interesting paper that appeared 3 months ago from Wang Yusheng Grom from Tianjin University in Advanced Science. Science, very good about the transmission from underwater acoustics and with experimental stuff. I know this paper very well because I read it at least a couple of times. Advanced Science, Wang Yusheng. You know him? He's from mechanics.
Oh, Yusheng. So he published or not?
Yes. He's very, very famous. Yusheng Wang, actually. It's a friend of mine, actually, because I did a lot of time. And we have like shared also PhDs and things like that, but we are not working on with him on underwater. And he published, I can post his, let me see. It's Yusheng Guang. You know him, of course.
Oh, I see.
Yes. He's Yusheng Guang, actually. So you know him, yeah. And if you see, I think it's Advanced Science, and that paper, I think, hybrid metasurface for perfect transmission and customized manipulation of sound across water-air interface.
Okay.
And so that's one of. Sorry.
Can you share the paper's name with me? Maybe the.
Yes, sure. Yeah, in the WeChat. Yeah, let me share the this, and then you can zoom. And I can do that.
Okay, great.
So it's not exactly the good, but anyway, you can find it in and there is no mini works on underwater acoustics. It's a very interesting topic, but there is not that many works on it. We are not working on that. There is a lot of application. There is the transmission from underwater to air, which is in which EM waves are struggling. So there are a lot of problems in that side. So the only way to me is to use acoustic waves and underwater waves for that. There is the problem of the cloaking, of course, or the acoustic clocking for underwater acoustics. Even if clocking is a kind of a hype since a while, but there are other solutions, other ways to do a kind, not a real clocking, but to be hidden, if I would say, to be not detectable, that doing clocking for underwater acoustic. I have some idea on that, but we cannot work really on that for the reason of the facilities and things like that. But it's not a very largely treated subject. It's very interesting. There is very few works. I don't know that much works on underwater acoustic metasurface. In that Nature Materials paper that you mentioned, in the perspective part, we have mentioned, it was in 2018 already, we have mentioned that one of the perspective is to work on underwater metasurfaces for transmission and things like that. And since there are very few works, but it's definitely very interesting topic.
Yeah, so actually we are doing some work about try to use underwater metasurface to improve the communication capability. So we already do some experiments to demonstrate some potentials. So we realized that the metasurface concept and also some devices is really useful, which is a practical application for underwater in the underwater fields. So that is maybe when you come to Qingdao, probably we can look at more details to discuss about some potential in underwater acoustics. So we believe that this field will have another great potential in underwater acoustics fields.
Absolutely.
Okay, great. So there's another question about you mentioned about this kind of metasurface structures. So one question is about have you considered about the material properties? For example, if your walls you use hard walls, right? All the materials you think that is a rigid body. So have you tried some? If you use the thickness of your wall is very very thin, becomes a relatively soft boundaries. So what will happen? so you for example you coupled with some vibration structure vibration modes coupled with acoustic modes. What will happen in this case? Have you tried?
Yeah, we can. Yeah, we have tried a little bit to see that vibroacoustic behavior actually. So yeah, actually, so we can get also, if we consider, for example, for absorption, it's not a good idea for absorber, for example, because you can have some leakage first, because if you have a really thin, and especially if you print your structure based on plastic, on PLA, it's lossy, and yes, you can have some leakage. But if you consider, for example, some metal, which is not that lossy as materials, that's very interesting to couple to consider the vibroacoustic absorption. This is one thing. Also, we are working on about simultaneous absorption of mechanical vibrations and acoustic waves, because usually they are not at the same frequencies.
Right.
You see, if you consider the same wavelength in acoustic and vibration mode, it's not the same thing. But you can have some mode conversion, you can have some vibroacoustic effect. But yes, we are looking at that, but not in separately for now. We are working on like acoustic absorber for not acoustic, elastic absorber for vibration. Actually, we have, you can see that maybe the paper will be today on ArcSieve. We have just submit a paper, which I think extremely interesting, about the elastic local resonance elastic metagrating by impedance modulation. We submitted it last week, and we submitted it yesterday to arXiv. So it should be today on arXiv about that kind of vibration absorption. Maybe I have to see if they put that or not. But
okay,
I can send you if you want the arXiv version. No problem.
Okay, I see. I expect to see that work, because we actually in the practical in our practical applications we see a lot of vibroacoustic acoustic phenomena. So that is why I asked this, whether how this phenomenon, how this effect will influence your absorption properties. Okay, so so your paper discuss about this kind of effect. Okay, so I
yes, it's mainly about the vibration absorption, not exactly the vibroacoustic, but it's how we call that locally resonant elastic metagrating. No, not yet on arXiv actually. So, but it should usually takes like 24 hours to have it on this, but
okay, great.
Okay, so it's absolutely great that we have some interesting point for further collaboration between France, possible in China. So in principle, we can even more arrange one more seminar in a week or in 2 weeks, because this actually acoustic seminar is a regular. It's every week. It's a weekly seminar, and also Yang Yao, maybe you can also give a talk, and maybe introduce it in details, and maybe Yang Yao, or maybe some other members of his group also can join this seminar. So we'll arrange kind of, so it will be really interesting. Let's
it's a pleasure.
Discuss it maybe in by email. Okay, at least it's 1 hour, 1.5 hours. So, and maybe it's exactly the time to proceed to maybe to short talk from Andrei Lutavinov, just to introduce the acoustic laboratory from the University.
Yes, of course. Yeah.
Could you estimate how much time does it take your presentation?
I think I need a few minutes. I will tell briefly, without details, just to inform about our areas of interest, and if Professor Assouar will have interest in some topics, we can provide details a bit later. So
okay, sure. So just I cannot. I will stop the sharing the screen, but I cannot do that. You can take the screen. Let me see if I can do that. You still have my screen, or?
Yeah, we still see your screen. Yeah. How can I? Let me try now.
Maybe here.
No.
But anyway, no problem. I will find that out. No
problem. How can we switch off the screen of Professor Assouar?
This is it. It's okay. It's fine.
Wait. So yeah, I will tell you a few words about our department, Acoustic Laboratory. I will briefly talk about our areas of interest, and I also would like to ask my colleagues help me during my talk if some details will be needed. Okay. So our department is rather young. It is about 2 years old. And nowadays there are a group of people who are more or less involved in different acoustic projects and problems. And here you can see professors, postdocs, PhD students, and students. And we are actively work to expand the number of participants of our team. So this list is dynamically changing. A few words about our research directions. We are working in the field of aeroacoustics, some medical acoustic issues, acousto-electronics, some questions of fundamental acoustics and optoacoustics, and I will tell about this direction a bit later. And a couple of words about our equipment. Here you can see a 2D waveguide, which is used for our measurements in audible sound. It has one movable wall here, so it could be configured for special needs. And also you can add or move anechoic triangles. Also, we have a mini pool for water measurements and underwater measurements. Yeah, also we use 1D waveguide, so-called impedance tube, you know. And also we have an setup for ultrasonic measurements in solids. So the first direction is metamaterials. Here you can see the noise insulation structure. All results are published here, but the thing is, and the main idea is that it works. Several mechanisms of absorption is used here. Of course, metamaterial principles and absorption in coupled Helmholtz resonators. And broadband noise insulation was achieved in this construction, and as I said, all results was published here. Also, we work on so-called meta-lens, which could focus ultrasound, and we are going to use it, for example, for high-intensity focused ultrasonic application. For example, in human body. The next task is combination of acoustics and signal processing. Here, colleagues recording the signals from lungs and heart, and then using signal processing, they were looking for some informative signs in the signals. To connect these signs with some diseases. Another interesting topic is is the task to provide the energy to for medical implants. So the idea is to use the energy of ultrasonic wave inside the body and to provide it to the medical implant, which is in the body. And for this reason, we are going to use some piezo transducers also for receiving and transmitting signal. What else? Some problems of fundamental acoustics. Here we observe high Q states in elastic medium or Biden states in the continuum. So, yeah. Could you say a couple of words? Mikhail Smagin is responsible for this task.
Okay, so yeah, we also starting to explore the labyrinthine meta-atom kind of direction. So it's kind of in its early stage. So basically, as a model problem, we kind of tried to experimentally measure the Kerker effect. The labyrinthine meta-atom can be, so it's kind of an analog of high dielectric particle in optics. So we can use its resonances to replicate a number of optical phenomena, and there was a paper about modeling and a theoretical paper on acoustic Kerker effect, and we just tried to measure it. Kind of to establish a technique of measuring such things. And now we are starting to do some more complex stuff. On the right, you can see that in optics, there is an established direction of analyzing, analyzing dipole-dipole interaction, so-called first energy transfer using the formalism of density of states, so we can use this meta-atoms to create this kind of mode structure, which we can modify and use this density of states formalism to theoretically and experimentally investigate how this mode structure modifies the interaction of speaker, which can be monopole or dipole, with microphone. So this is kind of in early stage, and so this is a slide.
Next slide.
Yeah, next slide. So this we recently published to arXiv and submitted. We also have a direction of acoustic forces. This is kind of again follows optical analogy. In optics, a lot of attention is paid nowadays in optomechanics to the different kind of directional forces like pulling forces or lateral forces, and in optics this can be done in numerous ways, like for example by breaking well, in general it can be explained by symmetry breaking, And theoretically, it is explained like by directional impulse. Directional impulse transfer. And this can be constructed by multiple interference, and in optics there was long established this kind of a correction to the term to the fourth expression. However, in acoustics, for some reason, it was not explicitly written. So we have done it and kind of reviewed this model problem of an isotropic particle rotated by some angle, which is the simplest case of symmetry breaking. This leads to this kind of asymmetric multiple interference pattern, which results in this lateral recoil force. And so we developed a theory for it. And however, in relay regime, such lateral forces are unstable. Next slide. But we also discovered that in Mie regime, if we go to Mie regime, there can also be stable configurations for such lateral forces. And actually, maybe they can be used for applications of sorting by particle shape, which is also kind of unusual, because in acoustics, this degree of freedom is kind of not very good explored. So yes, this is our recent archive paper. Yes.
Yeah, and as Mikhail said, we like to calculate and simulate different kinds of acoustic forces, and it could be used in special devices like acoustic sorters or acoustic biosensors and so on. So it's also a very interesting direction for us for investigation and so on. So Professor Assouar, that's all that we want to tell you right now. If you are interested in some topic, please connect with Andrei, Mikhail, Petrov, or with me. We can provide more details if you want. Thanks for your attention, and yeah.
Thanks. Yeah, I have just one small question about the last sentence on the precedent slide. No, the slide just before, about the degree of freedom in acoustics. What you said that there is not that much degree of freedom in acoustic to manipulate wave, right?
No, I said that particle shape. For some reason, it was kind of neglected, in the sense that like these sorting applications, usually they sort by like material parameters or particle size or something like this. But purely by particle shape, there is not that much papers about that. So this degree of freedom is not that actually used.
Yeah, actually, I didn't really understand here in this blood sorting application how sorting is done. What's the mechanism? I didn't get it actually.
So yeah, I haven't explained in detail. I can the effect is basically that if we build this, so what actually on the left, we pictured like these color maps. With color we show torque, and on the horizontal axis we have frequency. On the vertical axis we have angle of rotation of the particle. So this can be and if we look at the change in color, we can analyze the derivative of torque. So the condition for stable propulsion, stable lateral propulsion, if we have a lateral force, and if the torque has a correct derivative and it's zero. So basically we have such frequency windows, spectral areas, where we have the condition for this stable configuration satisfied. So basically this is calculated for a spheroid particle, but we can also do it for an erythrocyte or red blood cell particle, and build such maps too. And actually, yeah, such windows exist for red blood cell particles. But since white blood cell particles, they are not anisotropic, they are like approximately spheres. They are like spherical, more or less. They won't have such lateral force on them. If they shine, if they propagate a wave, it can be shown, it can be seen on the right picture, from the left. Since if on this frequency, if we propagate this traveling pressure wave from the left, the red blood cells will structure themselves to the angle of stable propagation simply due to Brownian perturbations. Well, not really, but since there is a torque, acoustic torque acting on them, they will more or less be around this angle of lateral propagation, and they will move both in the longitudinal and lateral direction. However, white blood cells, they will only move in longitudinal direction. So this is how sorting can work. Yeah.
Thank you.
Yes.
Sure. Very interesting topics.
Thank you.
So, dear colleagues, do anybody have some additional information or something like that? No?
May I ask a late question?
Yes, you've got 3 minutes, if it's possible, Sergey.
Yeah, I'm just wondering, so regarding this information about degrees of freedom, etc. So when you showed these labyrinthal types of absorbers, yeah, so they are not symmetric at all. Yeah, I mean, I understand that it was generated by deep learning algorithms, yeah, but for me it seems kind of strange that they are not symmetric, because well, usually you can expect some additional effects due to the symmetry of the structure, and
why?
Maybe the question,
why the symmetry can bring an effect?
I mean, I'm not sure exactly absorption things, but you know, if you consider some, for instance, simple models of two coupled oscillators, yeah, so you can expect some, I don't know, coupling effects which are stronger when they have when the resonators are similar. Yes. So
like constructive interference or something like that.
Yes, something like that. And I mean, it's have you considered to look in this way? So maybe just to consider transfer from symmetric to non-symmetric structure. So you have no symmetry at all. So no kind of.
No, actually, the very first structure we it was a kind of not symmetrical, but it was just a kind of perforated plate and just spiral, classical spiral. In that sense, it wasn't that random in the sense has produced, but it doesn't depend the symmetry or not on non-symmetry. It's just a kind of how you shape your resonators, and in absorption how you implement your thermoviscous effect, and that's it. And this geometry, the idea is go down the effective velocity of your wave. So it doesn't actually, the symmetry, if you can have symmetry or no symmetry, it doesn't actually anyway in that case.
Oh, okay, thank you.
So it looks like we can finish today's meeting. Professor Assouar, thank you very much for a very interesting talk.
And for your interesting talks too.
Great. So thanks for all of us, and goodbye.
Okay, bye-bye.
Bye.
Thank you.
Thank you.
Bye-bye.
Bye.